rose to. You know, it could go down to a different minimum.
But what if this is the only that possible?
We don't think that would be not. We do know that at infinity, the value potential goes to zero. So therefore, there will be an infinity at the very least. But maybe that we will not count as a minimum, but at any rate, that's a possibility. So the fact that the upper bound for the age of the unit, the dark energy, means it's not a coincidence. So why the value that the dark energy is close to our age is because we are towards the end of our universe, in a sense. That is, the age. The question of why do we live now is because we couldn't live any longer anyhow. The universe is coming to an end, I'm afraid. This would be one answer to the problem of why the dark energy value is close to the age of our universe. It's not a coincidence. It couldn't have been 10 times larger. We couldn't have been 10 times larger or 1,000 times larger. So with this dismal view, unfortunately, we may have to go 10 times, 100 times the age of the universe now is not too bad. But anyhow, I'm sorry to break the news to you that we may not last forever. Even though the estimates for these numbers make some assumptions, so we cannot be 100% sure, what we are more sure of is that it will disappear. That we are no doubt. Exactly what's the estimates and so on, we are still debating, and so it might be a bit longer or shorter, I don't know, but we do think that it will disappear. So let me tell you by concluding by saying that the strong ideas are beginning to be sharpened, extended, and better understood. They define some universal properties of consistent quantum gravitational theories, and they could have indeed dramatic implications about our universe and our existence. Thank you.
Thank you very much, Professor Lata.
A question. So Dr. Fanfa, so this string theory has been a still hypothesis, so it's more like almost it's true. I know like CERN has an experiment in 2018, but didn't find any evidence. But do you know what's the recent technology to make it to prove that it's true?
Very good question. Of course, we need to confront string theory with experiments. So I didn't mention it here, but there's one other prediction that we have made using these ideas, which is why the dark energy is so small. Why is it 10 to the minus 122? It turns out that value being small gets related to one extra dimension being large. And the extra dimensions that I told you are small some of them could be tiny, is not super small. In other words, we think there is one more dimension, the fifth one, one of the extra one, which is about a micron scale. That comes from the cosmological constant. In other words, the cosmological constant also comes with a length scale. I told you about the time scale, but there's a length scale. The length scale associated with the cosmological constant is a micron. And we think these ideas suggest that there's an extra dimension of the scale of a micron. Okay, how do you know this is true? How can you check it? Well, if you put two particles closer than a micron, then you're effectively seeing the extra dimension because you might be smaller than the size of the extra circle that you're in. So it looks like our universe will become 5-dimensional, not 4-dimensional space-time. And the 1 over r squared force law becomes 1 over r cubed. So the force between particles changes when they come closer than a micron. So experimentalists have already checked that 1 over r squared force law of Newton works up to about 30 microns. Interestingly, that's very close to the bound we're getting from the dark energy. And so we are hoping that if you extend the experiment further down, you could find it. Indeed, my colleagues are now currently designing experiments to push the 30 micron down to 10 microns. And so if we're getting close to the region where we could potentially see effects of string theory. So that's one way we could see it. Thank you.
Is there anyone has questions online?
Yeah, if your supersymmetry is correct, right? You think it's possibility to have another universe,
Have a what?
another universe in parallel?
We believe the number of universes with or without supersymmetry is finite. Supersymmetry is going to be much more restricted than non-supersymmetric ones, but we both believe both of them are going to be finite number. Now, it would have been ideal maybe to live in a supersymmetric universe. The universe would have been like constant in time and so on, nothing would change and so on, we'd be happy maybe. But we are not in such a universe. So, yeah, so I don't know what to say. I mean, you would have thought that if we had the choice, we would have chosen a supersymmetric one, but we are not in one. Now, we believe that it's in our universe, probably supersymmetry is realized, but at very high energy. That the energy we are talking about is broken, and just because it's broken means we're going to be unstable. And we might decay to something which is supersymmetric later on. That's a possibility. The possibility would be that we will go down to a supersymmetric one at some point. Not our universe. Question there too.
Fascinating talk, thank you.
Thank you.
Yeah, I have a question going back to the near the beginning of the talk. So let's say that Q equals M, and now we throw a massive charged particle with Q greater than M at the Q equals M black hole. Then don't we make Q greater than M, so we destroy the black hole?
So, good question. So it turns out that when you're doing the computations here, you have to be careful about the quantum effects, about how you actually compute the effects of the particles and the calculation of the charges. So, yeah, so there's some sort of.
Yeah, thank you very much, Professor Baba. Due to the time constraint, to take a group picture right now. So.
I have in the front, so people perhaps make money to leave in 20 minutes. Yeah. Thank you. And,
Thank you.
So everyone.那个 Bracken 的那个对你说一下，没有So everybody, no, everybody stand over here. So I need to have at least 3 rows. No, we turn it off. We're going to turn this off. Everyone. Oh, let's take it. 叫你第一排的可以蹲一下。对。我这是算你哦，那是在注意你那么另外一个，好，另外一个就扣了嘛，高的我们在后面嘛，前面可以蹲一排。
等会儿你往前，哦，我们自己的那个组委会和波士顿还有我们会员都站在后面走吧，然后我们波士顿的波士顿。
What's that? I do want. Okay. No, we can feed it. That's very interesting physics, by the way. I think I have to mute them.
Where were we? Oh, yes, we're on the moon, looking at Earth. And the Earth is quite beautiful, although it's only a small object in the sky. The sky is black because the moon has no significant atmosphere to scatter light. That gives an impression of how small our world is, but it's only a hint of how small our world is compared to the universe as a whole. If we look out at the sky with a powerful instrument, this is from the Hubble Space Telescope, and look at a small direction in the sky, small angle, and look for very dim objects, then the sky is no longer dominated even by stars. It's dominated by galaxies. You see here. Each of these galaxies contains something like 100 billion objects comparable to our sun. And there are about 1 billion such galaxies, or 10 billion such galaxies in the visible universe. So there are many, many solar systems. People now are discovering planets around other stars. They're very common. Probably many, many Earth-like planets out there. There's lots of empty space. We are very, very small on the scale of the universe. We're small not only in space, but also in time. One way to bring that out, because it's very difficult to conceive of such large times as we're about to discuss directly, is to project the history of the universe onto a single year. So just contract the scale of time so that we can visualize it. And the Big Bang starts on day one at 13 point, it corresponds to 13.8 billion years in reality. And various things happen. The Earth takes a stable form only on the 6th of September. Rather late in the history of the universe. And various on the 21st, that's not very far from when Earth stabilized. It suggests that life should be very common, that life develops easily once the conditions are even close to stable. Then various things happen. Life goes on. On December, Christmas, there's a gift. The dinosaurs start to take over. And they dominate the world for a while, the land, until on December 26th, they get to rule the earth for about 2 days. There's an extinction event when we now know a meteor or small asteroid impacted the earth, and no land dinosaurs survived. Dinosaurs still survive in the form of birds, but they no longer rule the surface of the earth. Oh, I'm sorry. That was a different extinction. The extinction event which killed the dinosaurs was on December 30th. So that's when mammals, not let alone humans, first came to have a chance to flourish. And all of recorded human history goes on in the last 1 second cosmic year. There's very good cause for humility. And that puts a lot of things in perspective for me. On the other hand, there's also very good reasons for self-respect that emerge from fundamental understanding of the physical world. This is a thin slice of a small part of the hippocampus of a cat, drawn by the great neuroanatomist Ramon y Cajal around the turn of the 19th and 20th century. This very accurate drawing is made using the technique of Golgi stains. This is a stain which is taken up by about 1 cell in 1,000, but the cells that do take it up get completely blackened. It's only by taking a thin slice of a small part of the cat's brain, and then taking only 1/1000 of the cells, that you can begin to discern the inner structure, the beautiful patterns that underlie information processing in a cat's hippocampus. So you should imagine a much richer structure inside your own head, and along with humility, there's a lot of reason for self-respect, because you have all these significant information processing units hooked up in very elaborate ways. And that's what makes us what we are. And already at the beginning of the scientific understanding of the world, Pascal got this spirit. He said, the spaces of the universe enfold me and swallow me up like a speck, but I, by the power of thought, may comprehend the universe. So humility is in order, but also self-respect. Another reason for self-respect is that we have power over the world through understanding of systematic technology and science. The per capita wealth of the world, of humanity, as you see, took off and is increasing exponentially. And if we don't blow it by going into climate catastrophe or nuclear war or some such thing, there's every reason to expect the wealth of the world to increase. So humility, self-respect, and then a third concept, chutzpah, which may be less familiar to some of you. This is a Yiddish word, chutzpah. It means audacity, for good or bad. Bravery, daring to take on the universe. And that attitude, which I've learned to take towards the physical world, is, and as you've seen, is that the most incomprehensible thing about the world is that it is comprehensible. We really do have laws that give us power over nature and let us do marvelous things. Explain the results of many, many experiments successfully. Most careful experiments we can, compare them with precise mathematical theories. We can also speculate about the ultimate fate of the universe. In this brief talk, I can only give you a tiny taste of what we know and what we've learned. In this book, Fundamentals, I've tried to do a digestible but honest and rich account of the fundamentals of our understanding of the physical world. Let me briefly describe what you will find inside its covers if you read it. First, an account of what there is. I've hinted at these first two themes. There's plenty of space and plenty of time, both exterior and interior. Very few ingredients. An objective measure of this is that you could encode the fundamental laws that make the universe as we understand it work in a very compact computer program without losing any information. So this computer program, which would be much, much shorter than the operating system of any modern computer, or an application like Word, if the computer was left to run long enough, would output the periodic table, the masses of elementary particles, and in fact, the answer to any question that so far experimentalists have been able to pose to nature. There's plenty of matter and energy. One measure of that is that the energy that the sun rains down on Earth, that great fusion reactor in the sky that generates so much energy, is about 10,000 times as much energy as mankind currently uses. And we're rapidly learning to exploit that economically using photovoltaics. And that's the long-term future, which is a very bright future. Unfortunately, the transition to getting there may be a bit bumpy. So, having given an account of what there is, then the second half of the book explains the history of the actual universe and where we are today in our understanding. We're not finished, but cosmic history is an open book. Cosmology now gives us a richly documented account of everything of the large-scale events in the universe, starting at roughly 1 microsecond after the Big Bang. Go past that, it starts to get a bit speculative, but we have a lot of evidence about the extremely early universe that's successfully explained by the fundamental principles I mentioned. We also understand why we don't understand a lot of things. So, for instance, the history of China, or of Sweden, or of the United States, they're all more complicated than the history of the universe. And the reason is that, well, we ask more refined questions, and there are mathematical instabilities that go, and just the dealing with many, many, many elementary particles in the real world that allow substructures to have lots of complexity, even though the fundamental laws, both as to how things work and as to how things began, are very, very simple. And then there's much more to see. We want to know as we refine our tools, we get more powerful at controlling nature. We can look harder and discover new things. Recently, the Higgs particle and also gravitational waves. There are prospects for solving some of the remaining mysteries. There's something called dark matter out there that's more common by weight than ordinary matter. The ordinary matter is what makes you and me, and it's biology, studied in chemistry and geophysics and all branches of engineering. That we understand very well. But just as we were achieving that complete understanding, right, remarkably complete understanding towards the end of the 20th century, the astronomers threw us a curveball. They discovered that there's other stuff out there that's not the same stuff as we're made out of. Doesn't have the same, nothing we know about so far can explain the properties of what they've observed. I think I know what it is, something called axioms, but that remains to be proved. And in any case, there are mysteries that remain. And then finally, I wanted to sum it all up, not just in terms of facts, but also in terms of meaning. And for me, one of the most profound pieces of wisdom to emerge from understanding the physical world is something called complementarity. So I'd like to conclude by saying a few words about that. Complementarity as a technical concept emerges in quantum mechanics, where it's really a theory. To understand quantum mechanics properly, you must use complementarity. But the basic concept, the broader concept of complementarity, was beautifully captured by F. Scott Fitzgerald, the famous author, even though I'm sure he was totally unaware that, of the word complementarity or that physicists were using it. He said that the test of a first-rate intelligence is the ability to hold two opposing ideas in mind at the same time and still retain the ability to function. That's what complementarity is. It's, as I said, in quantum mechanics, it's a theorem. And let me show you how that works. Simplified idealization of a quantum mechanical system, which is, however, not all that simplified. Suppose we have objects, they're quantum objects, so maybe I could call them quobjects, that have two properties. They have a property of color and a property of shape. And we can make measurements, we can make experimental measurements of either their shape or their color. And we can have theories of how likely it is that you'll find you have a bunch of these guys with different shapes, different colors. But, and this is where complementarity comes in, if you measure the shape, you lose all information about the color. And if you measure the color, you lose all information about the shape. You can't do both at the same time. You may have heard of Heisenberg's uncertainty principle. It's the same idea as this, but applied to more abstract things like predicting positions and momentum. So there are aspects of the world that you can understand each on its own and make complete understanding, but if you try to do both at once, it's impossible. You try to measure both at once, it's impossible. Now, a musical friend of mine, Nina Bohannon, suggested to me something quite profound. That is that there's a complementarity in music. When we have, and this makes it maybe a little more user-friendly and familiar. When you have music, especially if you have complex polyphonic music, there are two aspects to it. There's a harmonic aspect, which is how the notes playing at one time sound together. And then there's a melodic aspect, which is how sequences of notes make patterns that are somehow pleasing to the ear. And you can listen to the music either way, and you can analyze it either way. You can either be listening for the harmonies, and you can analyze it by harmonics, or you can try to listen to the melodies and listen to those. But it's very, very difficult to do both at the same time. That's complementarity. In fact, this example is remarkably close to what happens in quantum mechanics between position and momentum. When you have a wave function, the harmonic aspect is like measuring position, and the melodic aspect, which does global properties, is how reflects how you predict momentum. This example for Minna was more profound than she. I think this concept, although it's a theorem in quantum mechanics and a helpful principle in understanding music, goes very, very deeply and is very, very useful in resolving many kinds of issues that vex people. So on the one hand, as we've discussed, we think we have a profound understanding of the basic laws of nature, and nowhere in those laws does the concept of mind explicitly occur. There's no soul, there are no thought waves, and although people have done very, very delicate experiments of all kinds and have to worry about temperature, they have to worry about stray radio fields, stray magnetic fields, they have to keep things in a high worry about what people are thinking. So there's every reason to think that the physical world is governed by matter, and mind emerges from matter. And in fact, we know how to make minds that are good enough to beat us at chess or Go, that are definitely based on matter because we built it that way. On the other hand, if you want to interact with people and understand how they're going to predict their behavior in a practical way, you definitely want to say that they have minds and think about concepts that go with mind. So these are complementary ways of viewing the world. Both are valid in answering different questions, and a first-grade intelligence keeps both of them at hand. Another example is, I believe, is determinism and free will, which are often thought to be irreconcilable. Those basic laws of physics that are so successful are deterministic laws. They do, if you know the wave function, the state of the universe at one time, which is predict it into the future, projected into the future uniquely, or patterns of the past also on the earth. We all experience, well, I experience free will, and I suspect you do too. You make choices, and the basis of law is that needs free will. So both things are important ways of asking different kinds of answering different kinds of questions, even though superficially they appear to be irreconcilable. These are complementary. So complementary to me is a piece of wisdom that solves many puzzles and is mind expanding. It's an invitation to think about things in different ways. That's what it takes to be a first grade intelligence, according to F. Scott Fitzgerald. And I finally, to wind things up, I'd like to show you a way of getting beyond complementarity. In quantum mechanics, we can get beyond complementarity if we theoretically understand the wave function. That's the complete description. Experiments can only measure one or another aspect in any given realization. But if you have many realizations of the same object, the same physical situation, you could experimentally check either one. Or if you have it theoretically, you can just examine the theory and that you can answer experimentally all at once. That's kind of abstract. Let's listen to it in music, how you can transcend this duality between harmony and melody. Hope this was playing. I may have, fortunately, I will have to leave Zoom probably. So now we can see the melody. You can see it's deterministic in the sense it goes back and forth also. And we can also see the harmony at the same time. So with sufficient imagination and with the help of tools for thought, like our silicon friend here, we can transcend complementarity at the same time as we appreciate it. So I hope I've given you a taste of the many marvelous things you'll find if you look into my book, Fundamentals, and more than that, if you look into the world and appreciate it deeply. It's full of surprises, full of wonderful surprises. Thank you.
Very much, Professor Welchek. We can
Happy to take questions.
yeah. Okay, any questions?
Yes.
I was wondering, what's your philosophy in thinking that determinism and free will are largely incompatible? Actually, I just wanted to hear what you thought about this. So, I actually think determinism is necessary for free will because
Well, you're a wise man. That I don't disagree. The notion of free will is very hard to make precise and consistent. There's another complementarity there. You can make it precise or you can make it consistent, but it's very difficult to do both. Yes, just having randomness is not the same thing as free will. Sure. But free will is very difficult to define precisely, but sort of, I think we know how we experience the idea of making choices. And in law, we say that people have made choices, free will, and we hold them accountable if the choices are not good, unless they're insane, in which is the case that we said that was deterministic, they didn't get to make choices. so we need both concepts, and we experience both concepts, and they're useful in addressing different kinds of questions. So, okay. I hope that addresses. So yes, so I think the concept of complementarity doesn't necessarily give a unique meaning to the English words free will or the Chinese equivalent, but it illuminates the discussion very much.
From online?
Professor, so currently, there's a lot of breakthrough in physics, and many people say it's more fancier than fiction, like sci-fi. So what do you think is the next unimaginable thing will happen? Like the discovery is.
I think when I'm putting my money where my time where my mouth is, I think the most outstanding possibility that if you sort of have to multiply significance of discovery times probability of making it, I think there's a good chance we'll discover what the dark matter is. It's a new kind of particle called an axion. Those interact very, very weakly. They're predicted theoretically for deep reasons. In the properties in some detail are predicted, but the technology to detect them is only now developing. And I think on the time scale of 5 to 10 years, we'll know if these theoretical ideas actually describe the universe. Another great development that I'm not sure will be characterized by a sort of breakthrough moment. It may set in more gradually a series of small breakthroughs, is the prospect of having new kinds of computers, so-called quantum computers, that could be much more powerful at solving certain kinds of problems than the already very impressive computers we have today. Quantum computers should be very, very good at doing quantum mechanics, I think. And I mentioned that in principle, you could teach a computer, including any computer that's a Turing machine. They're all equivalent if you ignore the question of how long they take to do things. So quantum computers are still equivalent, but they're faster for certain problems. If we can teach the laws, the basic laws of the physical world to a computer without loss in a short program, much shorter than Word or a modern operating system. But it would take a very, very long time to compute the structure of a proton or something else. We do that, in fact, it's hard. But quantum computer could be much better at it. And so much better at designing useful drugs, useful catalysts, useful materials based on solving equations instead of guesswork and laboratory experiments. It would be presumably a supplement to those methods, but would be a very, very powerful help. Something like this has already happened in the aerospace industry, where people test out new designs on a computer for airplanes and rather than just guessing and taking it to a wind tunnel. And I think we can anticipate a similar development for chemistry and material science, at a much deeper level, if we can get the quantum computers working as well as they could theoretically. But the engineering difficulties in making such a computer shouldn't be underestimated. And I think you'd have to be very optimistic to think that quantum computers will do anything useful in 10 years. 50 years, I think it's like a 50-50 proposition. And in 100 years, it's pretty sure. Yeah.
Thanks, Professor. Share your fundamental insights. So I have a question. So what do you idea about the probability theory to help us understand the universe and the world? And we all know Einstein, he was pretty skeptical about that.
About what?
Use of probability theory to help us
Probability
to understand the world or the universe.
Well, probability theory is a very useful tool. Whether it's ultimately necessary, I think is not completely clear. For instance, famously, quantum mechanics in its conventional interpretations requires probability theory. But I think you can actually get around that by formulating things properly. The underlying equations in quantum mechanics, as I mentioned, are perfectly deterministic. But in practice, we don't have complete information. We don't have enough information to use the determinism to predict what's going to happen next, because we don't know what it is now. So that puts limitations on how well we can predict the future. This is a familiar situation even with predicting the weather. Yes, we could predict it if we had very, very accurate computers that and let them run for a long time. But in practice, it's very difficult, and we can make probabilities for how likely it is to rain or not. So that's what you get in weather. So probability is extremely useful. Whether it's fundamental remains to be seen.
Okay, we have time for one more question.
I think there's one question online, and yeah, I think there's a question online.
Okay.
One audience asked, what's your view about art versus science?
I think art and science are both wonderful. And I think the image that many people who aren't deeply involved in science, that it's a dry subject, that it doesn't have any imagination, that it's all sort of boring calculations, people turn off their human qualities. That's entirely wrong. To do first-rate science requires enormous imagination. You have to imagine how things could be different. Whether it's designing a bridge, might want to have special circumstances for each bridge, and also you can imagine maybe you can build an entirely different new kind of bridge that would be beautiful and useful. Or thinking about the fundamental laws. How can we do better than the current understanding? It requires a lot of imagination, because we already know a lot, and to imagine a way in which things could be different and better requires mind stretching and imagination. So I think mathematicians, physicists, even engineers too, are often guided by the same kind of aesthetic instincts that artists are. They're looking for things that sort of make sense, that work together, that form logical patterns. They're both human activities. And some scientists are also artists, very good ones. And some of them are musicians, or I'm an enthusiastic one, if not a good one.
Thank you very much, Mr. Grossberg. Thank you.
Okay.
All right, next up, we would like to introduce Mr. Li Xinqing to give us the winners for this year's outstanding awards. I would like to introduce the winner of the 2022 Outstanding Scientist Award,
member of the U.S. National Academy of Engineering, the Carl Richard Stolberg Professor of Power Engineering at MIT. Professor Gang Chen, welcome. Congratulations, Professor Chen.
Oh, just where else? Let me share my screen. Okay.
Hey, so let me first thank CAST for giving me this award. It actually made my last year suffering all canceled out. Thank you very much. And for the scientific part, let me make sure to say that this award is really for all the students and the colleagues I work with, so it belongs to them. And also, let me divide up the other half. That's half of my students and the people I work with, and the other half is my wife. And really, I have nothing. Okay, but say I actually hesitated when I got invited to speak here because I didn't feel I'd do much, at least last year. And but say I was told that I'm getting an award, I said I got to come. So here I am. I thought, say what I can tell you, all right, of last year and all my previous years. But I decided to share with you because I didn't go idle, and so I thought I'll share with you what I did last year. Of course, for I think most people here know that what happened, and it was a very stressful year last year. But I was very lucky. I had support of my colleagues, support of MIT. Basically, I decided that the best way to use this time is to learn new things. So I started learning new things, and I learned a few things I want to share with you. And particularly, I think here we have younger people, and I thought for me it was like a new graduate student and learning new things, and of course without a advisor, and with one colleague, that's my wife, and because for quite a few months I couldn't talk to anybody. I can't. I go to see lawyers, but I don't discuss my science with lawyers. Okay, so I actually wrote a few papers. I wrote more papers than I have read any other year myself. This is just to keep me engaged. And so it's nothing like a breakthrough. It's not getting me Nobel Prize. I'm very motivated to be here to people really getting this wonderful prize. But I do want to share with you the say the learning process, right? in fact, before this start, I was thinking about I want to check my research direction. I was summarizing my previous work, and this was one summary. Actually, this was a invitation from Nature Review Physics, and I remember after I was I'll say they learned from newspaper, right? What happened to me, and the editor actually reached out to me and said, she said, I was very grateful. She said, as long as there's no conclusion, we're still publish your paper. Okay, so I said, I better write the quick, and before there anything really bad happened to me. And eventually they published my paper, so okay, that summarizes part of my work. I was doing, so my previous work was working on solid, and I work in the heat energy area. So if you remember in high school, you learn heat has conduction, convection, radiation, right? So I was working on conduction. So I wrote all this, they work with, I worked also on electrons. So we worked on that. It's the atom vibration in solid, and then we work on how electron goes. But I actually was going to summarize. I said I'm not going to work on that anymore because for me it was the time to look into new things. But so I started looking into new things, and this new thing is not. Say, I haven't really worked a lot on liquids and soft materials, but I was talking to my colleagues and we've done something before on water, right? And I said, okay, maybe this is a real time to learn things about water. Water should be safe, right? They won't arrest me for learning water or work on water. So for the surrounding water is still cold. And that drew a lot of attention because they could use for desalination, they use for power generation. And for me, it was a curiosity. I say, okay, that's interesting, but we repeat the experiment and we didn't believe the explanation. So I come up with a newer, simpler idea. It's really simple. Just say, okay, the idea is that we want to create something locally hot, even though water doesn't absorb sunlight, right? So why don't I just flow some material on water surface that's flat, and that way they work. That was and I caught a lot of people's attention because it's simple, right? So everybody can go to the lab. In fact, I had students, high school student come to the lab, spending summer and going back and do the competition, science competition, got a various kind of so, but there is actually fundamental limit in that because the energy is conserved, right? So if you take a sunlight and they calculate how much energy it has in an hour, and then we know to evaporate 1 kilogram of water, how much energy you need. So you can easily do that energy balance and reach out that this is the upper limit of solar evaporation of water. That's 1.45 or around 1.5 kilogram per hour, right? And as I said, we published the paper, so many people jumped into this. I was puzzled, right? There are so many people work on this. But then there was another group. This was actually Professor Guifayu's group in UT Austin, and they reported something that was really strange. And they say, we put this hydrogel, so it's basically jello material. And they also put it under sun. They said we got 3 kilograms of water per meter square per hour, which is twice of thermodynamically possible, right? Because the energy is conserved. So I basically, this is because they published a paper in 2018, and I didn't believe in it. So we just ignored it, right? And but then I had the students coming in
and a postdoc come in, and he said that he wanted to do this kind of work that we're working on evaporating water. I said, well, there's this mystery, maybe you can go repeat it, right? So we started repeating it. And actually, I had quite a few visitors, so they are free labor, right? With visitor, we don't need a government funding. And I say, okay, let's explore those things. And at beginning, we couldn't repeat. So I pick up phone to and called Professor Yu at UT Austin. I said, can I send my guys here? And he was very generous, yes. So 3 of the researchers in my group went to UT Austin, spent a week, and they came back, they still couldn't repeat, right? But they brought a sample. And then we put it on a simulator, and indeed it happened, right? So it's like what they said. So we spent another year, say 3 months, actually, this is 2019. And we spent another few months just basically repeating their work, and eventually we can make the sample, and we fully believe in it. But what are the mechanisms, right? Because there's a mystery of energy conservation. If anything, right, the first law and second law of thermodynamics we heard actually entropy even today, right? From black hole entropy to when you do the CO2, right? So the thermodynamic law should be valid. We're not thinking that we're violating law, but there's a mystery, and we want to understand the mystery. We say, okay, rather putting on the sun, let's put in LED. So putting LED, and we see something very strange, different wavelengths of light actually evaporate different amount of water, even though the energy is the same. And the temperature also, when you turn on the light, the vapor is actually cooler, right? So you add energy in, you actually make it cooler, right? So those are the strange things that we saw. And we couldn't understand it. We had a lot of hypotheses, and at the end, we don't believe it. So, and Professor Yu had a theory, he said water in hydrogel in jello is different. So we said, oh, maybe he's right. And in that case, if water is different, let's do electrical heating. We don't need to put the sun, and that should reach that same result. So we spent 2020, right? That was very, the COVID start, and of course, all the difficulties. But basically a year of trying to do electrical heating and didn't work. And then 2020, 21, I couldn't talk to my guys anymore. And so I said, well, this is the time. Let me try to understand, right? When I was a professor, I was too busy. I was teaching, I was talking, but I didn't have time to think. Okay. And I didn't have time to really learn. So I said, now I got time. Nobody come to me for letters anymore, and no meetings anymore, no teaching. So I had really just to say all the time I can. So I know I can learn. I didn't know much about the water, even though you think you know water, but the water is, I learned that water, people say, is the most complex liquid. Okay. And I know very little about chemistry. I know very little about biology. I don't know biology at all. But I could access the internet, and I could access the MIT library. And so I was able to get all the free books online, and I started reading chemistry books, right? And there are many concepts that I know I heard, but I didn't really understand. Okay, so I used this time to learn. And when I was talking to my students, and I often repeat what my advisor told me when I was a student. He said, "You want to learn something?" This is Professor Chang Tian, and he was a Berkeley chancellor when I was his graduate student. Right? You want to learn anything? Write a paper. I give you 3 months. Okay, so I said, well, I got a few months. I should practice because I was telling my own student to do it, right? So can I do it myself? So I started really random. And this is this golden equilibrium that I know the learning, but I didn't know what it means. Okay. And of course, you start Wikipedia. When I try to learn hydrogel, it comes back to how many say, what is the donor equilibrium? We know the donor equilibrium between the cell membrane, there's a voltage drop, voltage between inside cell and outside cell, right? So that is really because the ions inside the cell and the ions outside cell, they are not at equilibrium, so there's a voltage across. And Donan's original study that's 100 years ago, okay? And he had a you got some molecules that are charged, but they cannot go through the membrane. And then you put the salt into it, and the salt free ions, they can move to the two sides. And he had a theory to say how much ions on one side versus how much ion on the other side. And his theory is based on, in fact, he wasn't writing clearly, but based on basically chemical potential. And I said I didn't understand chemical potential very well. But say, then I learned the chemistry, I write down every term, and there is a pressure term. So I'm not going to teach you the chemistry, okay? But I want to say there's a pressure term, and there's the electric potential term, and there's a concentration term. And Dolan just did a concentration term. And of course, there's the electric potential because from his concentration calculation, I know at the equilibrium, the chemical potential must be equal, right? So that's his theory was based on this chemical potential equal, and that will give you the concentration on the two sides, and he can calculate. But he forgot, he basically dropped out the pressure term. And unfortunately, over 100 years, people didn't include this pressure term. It was just surprising to me why people don't include this pressure term. So I was just wondering myself, I was reading, and I wasn't sure of this because I was just learning the concept, right? But then I read the paper, this was supposed to be authority, because I'm not in the field, so I'm just quoting, say, the journal, right? So this review paper say, Scotto is another paper. Scott's work in 2016 is the only correct complete theory on the donor equilibrium. And it turns out, as I was to say, what's Scott's paper, and they include that pressure term, right? They're doing different things. So, and but it turns out that statement was also not right, because even in the 40s, there was a paper that mentioned this. So I basically started evaluating how much it will have on the across the membrane potential. It turns out it's 10 millivolts. It could reach 10 millivolts. And we know across the membrane potential between the cells, it could be 80 millivolts. So normally 10 millivolts is not a small number compared to 80. So it's not really, we should not forget about it. And I also predict there's new voltage. But anyway, the reason I say this for particularly younger people is to say summarize, right? You learn, you summarize. I wrote a paper, I went 3 months, right? And this was actually the first time I tried to write a manuscript after I understood it, right? Because I was arrested in January, that's 3 months. Anyway, continuing, right? I was very grateful that another journal editor reached out to me. Actually, let me just say, this was the first, actually, there was an editor reached out to me, asked me to write a paper in chemistry journal.
I don't understand. I'm not working in chemistry, but I happen to work on this. Do you want to have this written up? He said, yeah. But after I wrote it up, I sent to the journal, and they sent out review, and the reviewer rejected it. So I had to find a different journal and to publish. There was another journal. I work in heat transfer, so heat transfer people didn't just discard me. Okay? And the editor came to me and said, "Can you write a paper?" He wrote me several times. And last year, I had all the reason not to reply email, so I didn't reply him. But after he sent a few emails, I said I should respond. So I told him, what about, I actually gave a talk in January, this was before it happened, to National Science Foundation panel. I said, let me summarize that, because I gave a talk. And said, yeah, you can write whatever you want. But when I was doing summary, I said, no, I don't want to do that, because that's the same sense I did before. And I want to learn new things. So I said, okay, can I write something on liquid? Review on liquid. I didn't understand liquid, and I tried to be an expert on that. So he said, yeah, write whatever you want, right? So I spent the month, read a few hundred papers, and make myself, basically I taught myself, I found that people really don't understand liquid. Liquid is very different, because I was working on solid, right? Liquid is very different from solid. Liquid is very different from gas. So I basically learned also what is water. Water is very complex. And I actually then come back to some of the understanding, bring me back to what's the best theory for liquid, and I form my judgment. So for again, if I have new students, so this is I say, okay, write a review, right? Review is a good way to learn the field, right? Start the literature, but critical. And I talk about hydrogel because all this was related to the work of the mystery of hydrogel, right? And I know the person who really founded the fundamental paper is Paul Flory, and he was another Nobel Prize winner. So it took me a long time. I had his book, I read a few times, I didn't understand, I guess too fast. And then last year again, I had more time, so I kept reading his paper and his book. And again, I'm not going to bore you with all the detail, but his theory basically starts from Gibbs free energy, and he has an entropy, basically all about entropy. Entropy when you mix water and polymer, and entropy when the polymer shape change. And then there's the enthalpy term. And then from this once the thermodynamic, if you can write those potential out, right, you can calculate the other quantity like the chemical potential and Gibbs free energy and chemical potential. And Flory, his book was very and I read his book and his paper, I still couldn't understand. But then I said, this doesn't look right, right? I know in thermodynamics, the thermodynamic potential Gibbs free energy as a thermodynamic potential, its variable should be pressure. And I look at this, I said, there's no pressure in this expression. So I went back to fundamental, and in fact, so this is confusion, not just me, right? When I read literature, I say other people are confused. That sort of confirm I'm not the only one. This was actually from also a very famous professor from Columbia, Van Mao. I read one of his very say, in the literature, it's not clear. So what's the swelling pressure? What's the osmotic pressure?
what's the matrix stress? So they're doing biology, right? So they're doing cabinet, right? Like I said, I know nothing about chemistry, I know nothing about biology, but all those just brought me to all those interesting papers, and that make me feel more comfortable that say I should really think and make it clear. So I went back to the basic thermodynamics, and I said that, well, I think Flores' starting point was not very clear. So let me start from clear thermodynamic theory, which is I consider hydrogel, which is at one pressure and the surrounding the different pressure, the liquid. And rather than write the Gibbs free energy, I write Helmholtz. Just trust me, this is say the right way to do it. Okay. And once I wrote down everything became clear to me. So I just summarize what's clear to me. I learned what is the osmotic pressure, and from here I can write down what is clearly the chemical potential of each species. So I can do the balance, how much ions on each side, the hydrogen side or on the outside surrounding liquid. And there, I apply this to the problems that I was interested in. Again, I practiced my local here. I learned from my wiser just to summarize it and write it up. So again, you can see the timeline. This is from my computer folder. I just say when did I start work on it, and I wrote the manuscript. And then gradually I have to finalize it and respond to the reviewers, and then eventually get it published, right? And so, but of course, coming back last June, I can talk to my end of last June through MIT, my lawyers. I could talk to my former students again, right? At the time, I no longer had my group. We work with other people, but the postdoc still persisted. But see, before I talk, of course I have time. I continue. I study. I said I got time. Let me do a review of what the other people have done, right, in this topic area. And to my surprise, because we spent a year to repeat the results of Hui, but other people have made many other materials working. And this is the Professor Yi's group, and those are the many materials. And I see Professor Yi Jin here, and then he was working on cow manure. Not many, I actually love that. But basically, you can make anything almost. And together evaporation above the thermodynamic limit, right? The problem is everybody just believe in Professor Yi's say theory that water is different in hydrogel, which I think okay, which I think is say water is indeed different, but I don't believe the energy will be that different. So I start to after I could talk to my group member, and I said he was continuing doing thermal evaporation and couldn't really break the limit. So I said, let me go back to the drawing board. I say, is there any other reason? Because now I know many other groups can do it, and we also saw this wavelength dependence before. And I see why this happened, why all this material, what they have in common. And the only thing that they have in common is the large surface area, because it's all porous material. And then I start to say, is there anything that on the surface between the light and the water that could actually lead to this? So this I saw Einstein's picture once, and let me bring another time, Einstein, right? Einstein had say, of course, we know what he got Nobel Prize for. That's the
photoelectric effect, right? He said, okay, when light comes to a metal surface, we can lock all the electrons. And in fact, the experiment was there. The experiment was done by Hertz. And but there was no explanation. So Einstein came up with explanation. So I said, could this process happening when light come to water surface? And light directly lock all the water molecular clusters. So one photon lock all the several molecules. So you don't need to break the bond of evaporating water. And there of course, there are problem. That's they say this is where the solar energy mostly in. That's a green light, right? And green light, of course, the water is clear. It doesn't absorb. So there's no absorption. It's different from metal. And the energy of a photon is very different between the water molecular bonds, right? Water molecular bonds, the hydrogen bond is 10 times weaker. So energy doesn't match. But by that time, I already learned that water has a lot of hydrogen bonds. They are really electropowerful. You can think of this as not just one single water molecule. They are clusters of water molecules. So if you have a photon that can lock all the many molecules together, and you break many bonds, that could conserve energy. So with that, I asked my students, I said, the hydrogen might be absorbing, because before we saw clear hydrogen. I said, why don't you dry it up and put a little bit of water there? So we still got a lot of surface. And see whether it absorbs. And indeed, once we do that, so we put a little water into hydrogel, it becomes absorbent, right? So that was so we found many other experiments. We believe this is what's happening, and we're still doing. We actually couldn't publish it. This is a very radical. We couldn't publish a paper, even though we did the experiment, and now we are still repeating the experiment, because the experiment also has a lot of delicacies. But anyway, this brought me to another thing that was just a thermal evaporation. Turns out that again, there are other puzzles, even just normal thermal evaporation. People measure there's temperature difference at say when you have evaporation, and even this is some kind of experiment. Nobody really believe it because there's no theory can explain it. It's simple evaporation phenomenon. We have a question. Yes.
Thank you. Quick question. Could you say again what you said on the previous slide about the experiment you ran and the thing you was trying to...
Thank you. I was jumping a little bit. So it's a piece of gel, hydrogel, right? And the water is so it's made out of polymer. It's made of water, and so here's the pure water. Basically, this is experimental error. It doesn't absorb light. Okay. And the original material doesn't absorb light either. So in theory, when neither of this material absorb light, there's no chemical reaction happening here. And they should, when you mix them, they should still not absorb light. But now, because I made a hypothesis, there's this physical process, light come to water surface, lock all the molecules at the surface, there's a surface absorption. So we create a situation where we dry the hydrogel, so there are a lot of surface inside, they put a little water inside, then there are a lot of internal surface between water and say the air. And in that case, we actually measure a very strong absorption, right? So basically, we create a material that create absorbing material from a non-absorbing material without a change in the material, and that is actually about very amazing. Okay.
Thanks.
And so this was just another history, and I saw. So the point I want to make is that there's so many things people don't really understand and just brush aside. And even this is simple thing like you evaporate water, you got a temperature difference, and because people couldn't explain, and a lot of people don't believe it. I say, okay, because I was working on electron before, I was working on lattice vibration. I know actually how to create the interface temperature jump. So basically I developed a theory and I was able to, I think I was able to explain the experiment. And that led to another paper. So I'm sharing with you the, say, during this time, I was, but in fact, they for this is for younger people. Then I was actually working a lot, I was writing a lot. Now this published was just a, but the good thing is it's a notes in my computer. I can go back at any time and pick it up, right? So some of those are still hung me, and I haven't finished some of this. We put it on say archive because we're still working on it and we couldn't publish, so we just put on archive. So with that, let me just finish this quoting a few people here, and we cannot. See, this is the brown timing, right? See, first I want to say, for me, the man, the human, is not just man. The woman could be he, right? She, and they. But a man is not made for debate. A man can be destroyed, but not defeated. And let me, for me, it's really my colleagues and people saved me. And when my colleague York, the day I was arrested, and he organized slides and wrote the MIT open letter. And really, that is the event that changed the whole history, I think. Say that certainly impacted me, but I think it indirectly impacted many people here. Okay. And finally, I want to quote this. This was a colleague, African American colleague, that he sent me last December, right? And this was Martin Luther King's writing when he was in prison cell. And his writing is injustice anywhere is a threat to justice everywhere. So with that, let me thank Castor for your kind invitation and the award. And thank you very much.
Thank you, Professor Chen. We have time for 3 questions.
Science question.
Actually, but my research in microfluidics, and actually I've noticed in the past 5 years, suddenly the hydrogel becomes super popular. Since you also talked about hydrogel, can you also give me just some idea why suddenly hydrogel research becomes so popular?
First, I'm not an expert because it's popular. I guess say I have a few colleagues that really influenced me. My good. In fact, he's a big expert in hydrogel, and I can say that they have a lot of really advantage for human electronic interface because the hydrogel is very compatible with biology, right? So there are say a lot of interest in that. For me, it was like because I was their colleagues, as I learned a lot from them, talking to them. I said I got an interest in that, right? So when I saw they put a hydrogel evaporate water, I say that's a thermodynamic puzzle, right? And you don't have many thermodynamic puzzles now, right? And so I said I want to understand. That's how I got it.
Thank you.
Yes,
I want to say, so I was inspired by your carbon foam, what it decided to work a couple of years ago. So that work led me into this field actually in the past 2 years. And these days, whereas my research group, at Northeast University is still trying to explain the fundamentals, about water desalination. One of your slides showed us there exists a mismatch in energy. So for this hydrogen gel, for the hydrogen bomb, actually, the energy balance, the energy is about 0.26 electron volt. And also, you also mentioned that actually in one of your published manuscript on archive this year, mentioned that actually the green light of around 550 nanometers actually corresponding to electron volt of about 2.5 electron volt. And also here you mentioned energy can be matched by accepting clusters. Can you explain a little bit more on the clusters?
So between so one water molecule is bonded with the four ideal case, four surrounding water molecules, and each bond is about 0.25 or 0.26 electron volts, right? But now, if you take many molecules, those molecules will bond with the surrounding molecule, right? And they count that bond. We actually still don't know how many molecules we're cleaving off. And but see, there are many other bonds, right? So bonds always have energy. So if you have n times whatever energy bonded, that can match 2.5, right? So that's the energy matching. So if you are cleaving off many other bonds, at the same time, that we think that could meet the energy requirement. We are still, there are a lot of mysteries. We still doing a lot more experiment trying to understand whether this picture is true or not. Yes.
So, if I heard you correctly, basically your theory is that we have a photon and it comes in and knocks off like a whole bunch of molecules at once.
Right.
One photon. So how does the hydrogel help in that process? Because you mentioned that like
very good question. And in fact, once we think this is the process, we say because in fact this is what really, right? At the beginning I was just looking at the polymer, right? I realized that now people have done many things not a polymeric base, and it's really just surface, right? So what hydrogel, all this materials create a lot of interface between water and vapor. So light going into the water surrounding, so it has a potential lock out this, but there's no room for them to go. So that process doesn't happen. But at the interface, you got the adjacent vapor, which is very empty. So you got a space for it to go. So that's basically so you don't need the hydrogen. You just need a structure. So this could have a really big impact because you think about the water, right? You think about clouds, you think about the earth, 70% covered with water, and you think about the clouds, right? And it's all interface, water droplets interface. So we believe there is this big missing piece. People have not incorporated any of the current model on climate and so we're evaluating all those potential impacts.
so essentially it's surface area.
Yes, it is surface area, but then the earth covers 70%. Pretty large surface area. I know. Think about that's actually not large yet. So if you think about the droplets, so many surface area.
Fascinating. Thank you.
Thank you.
Thank you very much, Professor Chen. Okay, we will have a 5 minute short break. Then we will have 2 more award speakers and then have lunch box for everyone. So yeah, let's break for 5 minutes and then come back.
Thank you.
自民医院的专家以及先进的影像放疗等大型设备，建院以来，成功的震撼了众多疑难病例。我们愿意为你排忧解难，帮助照顾好您在国内的亲人。
这个还要再放吗？还是放下一个？
放下一个。
北京美中爱瑞肿瘤医院。
对，有声音了，把这个拿走就行。
Hi everyone, this is Dr. Min Sun. I'm a medical oncologist at the University of Pittsburgh. I also serve as the Chief Medical Officer for Beijing Area Cancer Center. It's my great honor to represent all my colleagues from Area to congratulate and celebrate 30th anniversary of CAST. Area is the only private tertiary cancer center in Beijing. We offer one-stop service for all patients come to our area. Please see our short video and flyer. 艾瑞竭诚为您和您在国内的亲友服务。Hi everyone, this is Dr. Min Sun.
北京美中爱瑞肿瘤医院是一家坐落于北京的3级肿瘤专科医院，长期与美国匹兹堡大学肿瘤中心深度合作，致力于提供国际水平的肿瘤诊治的医院。医院拥有来自于协和、北大、人民等知名医院的专家，以及先进的影像放疗等大型设备。建院以来，成功的治理了众多疑难病例，这其中包含很多海外华人的在华家属。如果您有需要，我们愿意为你排忧解难，帮助照顾好您在国内的亲人。
有点太匆忙了。就是您是其实善解人意。所以你做企业成功是有原因的。对，因为你这个企业家还是要有很高的这种，我觉得情商还是要很高的情商的。对。对，您
congratulate and celebrate
这个对，从你这个
Area is the only private tertiary cancer center in Beijing. We offer one-stop service for all patients. Please see.
大家好，我是沈路，旅美科技总。
还有一个，后面还有一个广告，你那个公司的广告，往下翻嘛。
亲爱的旅美科，大家好，我是。
这个。
介绍 TileSec 全基因组测序试剂盒。转做酶关联长农场测序是一项操作简单且容易扩展的新一代测序建库技术。它可以为全基因组规模的测序应用生成具有标签序列的 linked arrays。使用 TileSec 全基因组测序试剂盒，仅需3小时，研究人员便可以在单个 PCR 管中构建整个基因组轮廓。在 PCR 管内，树叶有独特。标签序列的子株，以子株表面有相同而独特的标签序列。这些标签序列对 DNA 长片段进行编码标记。经过测序后，便可获得长片段 DNA 信息，从而精确地组装从微生物到人类的各种基因组。致力于新型长度长测序技术研发的无锡普惠公司推出的 TileSec 全基因组测序试剂盒，可以将转做酶合成为转做子的 DNA 片段形成一个复合物，称为转做体。转做体与样本 DNA 以及子株上的标签序列反应相互附着聚合在一起。加入第二种转做酶，将另一文库接头标记连接到 DNA 转做酶复合体上，在标签与接头插入之后，附有标记过的 DNA 的子株经过洗涤，随后通过几轮 PCR 循环扩增，将有标签序列的文库 DNA 从子株上释放出来。整个过程操作简单且经济实用。TileSec 反应既可以在单个0.2毫升 PCR 管中进行手动操作，也可以利用自动化设备进行大规模项目。2代测序与传统方法相较，有以下几点明显优势：de novo 组装、结构变异、基因分析、宏基因组学研究。用2代测序平台进行长片段测序，比3代测序更精细。等效测序长度大于50 KB DNA 片段 ，DNA 需求量低至0.1至5大克 ，de novo 组装、结构变异、基因组分析、宏基因组学研究。经过国际领先的2代 NGS 仪器厂商 Illumina 多次验证 ，TileSec 技术适用于不同微生物测序和基因组 de novo。
他那边 share 了，我这边就不能。那一会儿吃饭的时候再放2遍，放2遍。
我把你以后你把那个。
Please don't relax your feet. Yeah. So we have a lot of time to mingle later. Please. Okay, let's welcome our next award speaker. He's the winner of the 2022 Science and Innovation Award, investigator of the Howard Hughes Medical Institute, the Fred Rosen Chair Professor of Genetics at Howard Medical School and Boston Children's Hospital. Professor Yi Zhang, welcome, Professor Zhang.
Thank you very much. Yeah. Okay. It's a great honor to get this award and to be invited to give this talk. You know, as you can see, you know, this is quite diverse subject and topic from mathematics to physics to engineering. Now I'm going to talk about something related to life science and medical science. So one important difference, you know, unlike Professor Chen, he can in 1 year, you know, write many manuscripts, publish many papers. So what I'm going to tell you, this is totally different ballgame. So we need many people who come many years to publish one paper. That's the difference between biology and medical science and other science. Okay, so that's why I'm going to basically kind of like in summary of my career. Okay, so far, talk about in the last 25 years or so, you know, of work. So he can talk about, you know, 1 year's work. Okay, I need to like tell you like it was quarter a century work, many people, almost 100 people for work. Okay. So anyway, so basically, you know, very basic. And this is related to every one of us, right? We basically, our body is composed of many different cell types. So what I show you here, 200 cell types, this is the 12. You know, nowadays with single cell technology, you know, this number probably has to minimum times 10 to 100. Okay. So because more different cell types are identified. You know, different cell types, as you can see, they have different shape, looks different, they function different, but they are all composed the same genetic material. The genome. So three pairs chromosome. All our genetic information are stored in this 23 pairs of chromosome. So if you ask what is in the chromosome, so basically it has DNA as well as some basic proteins. So this is the, if we, you know, from chromosome going down to the more details, you will see basically it's the DNA and the histone. So the basic building block for this
is called a nucleoside. Okay, so this thing. So basically, it has a ball-like protein and about 200 base pair of DNA wrapped around. So that's the basic building block, just like bricks when you build a house. So that's our genomes. And this is what is shown. This is the building block. So on this building block, it's the histone octamer of the protein that has 4 different histones. They all have a common thing. That is the histone 4, like a ball. Then with 2 different pairs, means N-terminal and C-terminal. So this is the proteins. So in a nucleosome, this is what it looks like. The ball-like, core histones, then DNA wrapped around this ball, and then unstructured C-terminal, N-terminal of the histones. So one important thing of this histone, unique thing, is that the N-terminal, C-terminal has many different chemical modifications. So basically, chemical tags are attached to the different amino acids of the histone pair. So basically, some of these modification of chemicals are inheritable. Okay, so then epigenetics, that's my field, is the study of heritable change that do not even change in DNA sequence. So we all know genetics is the study of the DNA sequence base pair. It's the DNA-based inheritance, that's genetics. But the epigenetics is a study that do not involve a DNA sequence, but rather involve a modification or on histone or DNA. Okay, so that's called epigenetics. EPI is coming from Greek word. That means above and beyond. So these are beyond classic genetics. Okay. So why, epigenetic study is important? So why? Because it's play a critical role, regular key steps of the central dogma in molecular biology. So the central dogma meaning, from genetic material DNA that transcribed to make RNA, then RNA through translation to general protein. So these are the very fundamental basis of all the biology and the molecular biology. So epigenetics, through those modifications, play important role in regulating this step in transcription step. Through regular transcription, it's pretty much control the gene expression. That's the main controlling point. So therefore, identify the enzyme that make those modifications on histone or DNA is critical, right? Because this modification, change gene expression. Gene expression controls how much RNA and protein are made, and that determines a cell's property. So therefore, identify those enzymes are important. So in the past 2 decades, or more than 2 decades, these are the enzymes that modify histone DNA that we have identified in the lab. Okay, including enzymes that remove acetylation, enzymes that put a methyl group, enzymes that remove the methyl group, and enzymes that play ubiquitin histones, or the enzymes that remove the methyl group. So I'm going to quickly summarize, those work, including how we biochemically purify these different enzymes, and also our recent discovery of different new kind of genomic imprinting, and how that might contribute to the animal cloning. And then at the end, I'll quickly summarize our efforts in translate what we discover into treatment okay, particularly for cancer. So this is the year that I start my independent lab. That's 23, 24 years ago. So at that time, we know that the histone tails indicated here, these are different amino acids, are subject to methylation, indicated these are lysine residue, have the chemical methyl group. And we don't know what the enzyme responsible for this. You know, if we know what enzyme responsible, then through study the enzyme, we can know what this modification are doing. Okay. So we took a biochemical approach. In biochemical purification, basically you use a substrate, that's the histone. Then we put a treated stem, that's the daughter for the chemical group, methyl group. Then ask which fraction of the proteins that have the enzymatic activity. So through a assay that you can see if this fraction has the enzyme will transfer the methyl group from treated stem to put, you know, into the substrate to make it hot. Okay, so you can see from here, there's a different fraction that has activity. If you have activity, you see a band here. Okay, so basically through a lot of work, many people work in cold room, take the protein extract and fraction a different fraction, and then each fraction to see which fraction has enzymatic activity. Then in a few years, we identify 6 different methyl transfers. Okay, that has enzymatic activity to put a methyl group in different lysine residues, different histones. So this is how we identify enzyme. So one of the important one later on, I will mention again, is the called EZH2 or Onicam. It's a specific methylate to put a mark on H3 lysine 27. So later on, we'll come back. Well, apparently, after we found the enzyme that put the mark on a specific protein, the next question is that is there enzyme that removes the mark? Okay. So then we started to ask whether this methylation is reversible. So can we found an enzyme that's methyl enzyme for the group and also remove the group, then that's regulation. If you only have an enzyme for the group, there's no regulation. And gene expression needs to be tightly regulated in order for us not to get a disease, develop properly. Okay. So that's the question. So how we do that? Because we have no clue. At that time, no enzyme, for histone remove this. And we know we have no clue what kind of factor needed, what kind of condition you need. So we basically, through reading other papers, other studies, get some clues. So what I show you here is kind of a chemistry of a DNA repair. These are DNA base, and this actually is not normal base, body. So this methyl group actually it needs to be removed. Then it's normal base. So this DNA repair reaction, the protein for the RKB, it needs iron and alpha ketoglutarate as the core factors, and alpha ketoglutarate and generate succinate and release formaldehyde. So basically, this is somebody who started DNA repair, demonstrate this. Then we look the chemical property of histone demethylation. So basically, this is the histone lysine residues. The methyl group are attached to nitrogen. If you look, this thing from chemistry point of view, both need to break a carbon-nitrogen bond, okay, to remove this methyl group. So we assume if there's a histone demethylate, you should be used similar chemistry. So therefore, that's why in our assay, we put the iron, and we also use alpha ketoglutarate as the core factor and monitor the release of formaldehyde. Okay, so basically that's the hypothesis. We didn't know whether it worked out, but it worked.
So that's how we set up an assay and purify the enzyme. And at the end, we found this protein that people never not much of study. There's many different domains, and through deletion mutation, we show this domain called the Jumanji C domain is important for the enzymatic activity. If we mutate it, it's going to kill the enzymatic activity. So this pretty much defines that this motif, protein with this motif are likely to remove the methyl group. Okay. So this is about our discovery of histone method. Now the next question is that is whether DNA methylation are also can be removed. So let's ask the question about this. Again, we took a similar approach, looking at chemistry. So this is methyl cytosine. It's the base of DNA. It has a methyl group. So after I remove this methyl group, it generates cytosine. Okay. So again, it is similar to the histone method, but there's a difference. The difference is this is the carbon-carbon bond. The other one carbon-nitrogen bond. So the chemistry is a little bit different. So look into all the literature of previous studies, there's one reaction are similar. That is the uracil, that's the base in our body. Synthesize requires, basically from thymine. Thymine is the normal base. And thymine to uracil conversion, if you look at the chemistry, are quite similar. Also requires the remove of the methyl group that's through carbon-carbon attach. So this is the known reaction in the fungi and parasite. Okay. So remove of this methyl group that attach the fire position of the pyrimidine ring. This is very similar to this. If you look, the difference is this is the amine group, this is the oxygen. But chemically, these two should be very similar to break the carbon-carbon bond. So in this one, there's two enzymes involved. One is called the thymine hydroxylase. Through three itinerary oxidation reaction to generate this methyl group, generate hydroxymethyl, formal, and carboxyl, and eventually decarboxylase to remove this. Okay. So bottom line, if there's a DNA demethylase, then the likely mechanism will be through itinerary oxidation, then a decarboxyl remove the carboxyl group. So basically that's leading us to looking for enzymes that has probably thymine hydroxylase. So this leading to our discovery of the TAD family proteins. And we show that TAD protein can take a 5-methyl C as substrate and convert that to general hydroxymethyl C, the first step. Then we continued and demonstrate this TAD protein not only general hydroxymethyl C, also general formal and carboxyl. So basically, it's similar to the proposed mechanism that I showed you earlier. Well, like many other things that when you discover somebody else will also discover. Indeed, and your Rose group reported have well needed hydroxymethyl C generation even before us. So basically, these are the three kind of class of enzymes that we studied and identified. And so after that, the majority modification that is on histone and DNA, the enzymes that add in the group, the enzymes that remove the group are identified. So therefore, we have to change our strategy, basically what to study. So what to do? That's like more than 10 years ago, we decided to looking for, the function of different modifications in pre-implantation development and somatic nuclear transfer program, the cloning. Why we pick up that? Because during early development, the chromatin is very dynamic. Imagine the sperm and egg, they are very, very different. Not only look different, how DNA inside the cell, the sperm and egg are packaged very different. So therefore, their modification, their chromatin structure are very different. Sperm don't have much of distance. So, but the eggs, the DNA wrap around with distance. So we thought that the early development when life start, okay, it's important. Anything wrong there will be no normal development. So that's why we pick up that discovery of non-canonical genomic imprinting. Later on, I will expand what is genomic imprint, and then also identify the barrier and overcoming the barrier for cloning. Okay, many people basically take your cells, you have all the genetic, and make you. Okay. Theoretically, it's not enough. So basically, now I want to introduce to you the early development. Okay, what happened? So basically, the egg, right? We need egg and sperm to make a human being, make any animal. So in the egg, mature eggs, I'm to arrest it. There's no transcription, no gene synthesis. We can just, that's why egg can sit in there for a long time, okay? But after fertilization will trigger the eggs being activated and inter-cell cycle, okay, stop. And during that, after activated by sperm, then the egg, the many RNA inside the egg will start to be degraded. Okay? They are not needed. But the genome and the DNA will be activated to generate new transcripts. So new transcription, because you need those newly transcribed RNA to make a protein, and the protein needed during the whole developmental process. But the question is, how the zygotic genome activation takes place. So basically, in mammalian, it's not known. Imagine we know science, so we can go to Mars, go to moons, but we don't know how actually when we start sperm trigger egg, what gene get activated and how they get activated. So those are fundamental questions. What the factor involved. So we want to, this is actually just recent few years to address these questions. So we take advantage of. You have a question?
Yeah.
Can we later on you can keep that because if we stop on this part it may drag on. So after I finish we have a question session. So basically in order to identify the factors that trigger the first transcription activation when our life starts. So we took advantage of the fact that I mentioned earlier on, in our genome, right? The whole genome is, wrapped around by the histone DNA wrapped around this. They are uniform and distributed like this. Every 200 base pair, you have a nucleosome. However, in the transcription regulated elements, those places enhanced and promoted, they normally do not have this. So therefore, these DNAs are easily activatable by DNAs. So because of this property, we decided to use DNase 1 to add to this. So then DNase will cut this DNA to generate DNA fragments. And these are the transcription regulator elements. And then if we put a tag on this DNA, we can sequence them. Then generate the whole genome, which part of the genome are accessible, are responsible to regulate gene expression. By this way, we can identify the whole genome, wherever, which place are regulated gene expression. So by this way, we applied this technique into different embryos from one cell right after fertilized, then 2 cell, 4 cell, 8 cell, molar and blossom stage. Okay, we are specifically focused on this 1 cell to 2 cell transition, from 1 cell to become 2 cell. Why? Because ZGA, if you remember, I mentioned earlier on, that happened at 2 cell stage. Okay, so what we do is to compare the openness. 1 cell there's no open, not open. In 2 cell, the chromatin open, and those are the responsible to transcribe inactive the ZGA gene. Using that way, we identify the first mammalian transcription factors, NFYA, are the important factors to trigger the gut genome activation. Because if we knock down, get rid of this protein, those genes that cannot open the chromatin, they cannot be activated, then the embryo will arrest, cannot move on, develop. So on the other hand, we were also curious, the sperm genome, which are tightly packaged like a ball, with protein, not even histone. Well, the egg genome is like normal nucleosome, it's more accessible. We want to know when, after fertilization, how long it takes for the male and female equal, because genes need to, basically we have two copies. One copy of genes is from your father, one from your mother. And the majority of them need to be expressed equally. So basically we want to know, so basically we found that these two paternal maternal 6 cells of the sperm and this, then they are equalized, as you can see. The maternal and paternal allele, their chromatin accessibility are equal here, and you cannot see the difference. However, there's a number of genes they show only one allele, either from the mother's allele or from father's allele are open or expressed. Okay? So this property making us ask, can we use this property to identify more imprint gene? Imprint gene means a single allele expression. Okay. So this proves the concept of genomic imprint. So what is genomic imprinting? We all know if you use the sperm fertilize the egg, then you can generate animals in mouse. Okay, but if so about 40 years ago, these two scientists, Azim Surani and Dov started performing interesting experiment. So you have the one from father, one from mother, genome, right, after fertilize. So what they did is they swap these two pronucleases and generated like this embryo contains. So basically, this embryo contains 2 copies of genome from mother. This one 2 copies from father. Guess what? Do you think it's enough to generate a animal? No. So basically, single parent cannot generate a normal child. Okay, that's 40 years they perform the experiment. What does that mean? This means, from one parental genes cannot have all the genes needed expressed for driving the whole development process. Meaning some genes only either express in father's DNA or mother's DNA, right? So that's why you need both driving the whole process. So for this discovery, they received the Canadian Gardner Award. So what's the mechanism underlying this? In the past 40 years, people has understand the main reason for that is one of the ideas is silence. Okay, so basically in our body, in any cell, 99% of genes, there's no difference from your father, from your mother, both expressed. So those are called biologically expressed genes. On the other hand, there's 1% of genes. This is the data from mouse that only express from one allele, that either express from father's DNA or from mother's DNA, and the other copy are silenced by DNA methylation to put a methyl group in the DNA. And so this phenomenon is called genomic imprinting, and the silenced allele is called the imprinted allele. So, whether we can find more imprinted genes in addition to gene methylation, because people found that there are other genes, there's no difference in gene methylation, but they show a single allele expression. So what we did is perform similar experiment what they did before. Swap these 2 pronucleases and make androgenic and pathogenic embryos. Then we perform a lot of different assays. No input DNA is one sequence. Okay, so this one allows us to identify which allele parental, mother or father allele are open. Okay, then RNA stage is to look that expression is from father allele or mother allele expressed. And WGBS is look their methylation, whether this linked to DNA methylation or not. Through a integrated analysis of all these data sets, we identify 76 new imprint genes. That means before our study, people do not know these genes are only one allele expressed. Okay, and we also found some non-coding RNA, also one allele expressed. And more importantly, none of this shows gene methylation difference. What that means is there's another mechanism that mediates this mono allele expression. So what's the mechanism? So we basically cut it long story short. We already know what's the mechanism. That's the 27 methylation. I mentioned earlier on, we are the one discovered the enzyme in EZH2 methylation 27 of H3. So we figured the mechanism. What happened is that during oogenesis, during the egg formation, then this female allele from mother allele, they have this marker, okay, during oogenesis, and then they have these chemicals put in those genes to keep them silenced. So therefore, the mother allele will not expressed before implantation. So after implantation, the embryo is lost, but the actual embryonic placenta they maintain. And these genes are important for the placenta development. Okay, so in the past several years, we actually understand the function of this non-caloric imprinting. It's very important for placenta development. It is also important for imprinted X inactivation. So basically, what X means, the females have 2 copies of X chromosome, and males and men have only 1. But many genes have to be equally expressed. So therefore, 1 copy of the female X chromosome has to be silenced. Okay. The mechanism of silencing is for use the new imprinting mechanism that we discussed. Okay. So then it's also important for cloning, animal cloning. So why I will tell you later. Okay. So basically this brings the cloning. So many people know the dawn is the shape. That's already 25 years ago people published this. So basically they can take a somatic cell from, take your skin and put it into an egg. Then they can grow up and generate new, animal or new. So basically in this case, the dawn is the shape, but the cloning efficiency is very low. They use 277 eggs, but get 1 animal. So the cloning rate is very low. Okay. So why? This is because during the cloning, almost many different animals, like mouse in this case. So total term is less than, if your technique is very good, you have 1%. If you 100 egg, 1 goes there. But if you fertilize, the majority of them will make. Okay. Unless you have a sperm or egg defect. Right? So what is the barrier? Why cloning do not work efficiently? So we basically this can tell you, in mouse case, if you, so these are the embryos. If you do IVF, means sperm fertilize egg. So during pre-implant development, almost no drop. Okay, 95% will make it to blastocyst stage. If you use somatic cells to do this, if 2 cells is where the GA, 4 cells already dropped. So there must be something events before 4 cells, run. Okay. What is before 4 cells? Is that you got a genome activation I mentioned earlier on. That's very important to drive the development. So bottom line is whether The reason that you have no cloning rate is due to the VGA problem, like that genome activity. The answer is yes. So we basically figure out the reason. We published a few years ago. So what happens? Sperm and egg, during their development, they are reprogrammed. The development genes are forced to be activated. On the other hand, in somatic nuclear transfer, so the somatic cells are permanently differentiated cells. Okay, permanently differentiated. They are silent, their development genes are silenced. If you put that into this egg, they cannot be activated. So because of this silencing, we can play a trick to use a demethylase to remove this barrier, then leading to successful VGA, then develop. Okay. So we also show that this thing can work in human, because if you do somatic nuclear transfer and use this kinin demethyl, remove this barrier, then it can develop the cluster from which you generate human ES cell. Okay, and that one can be used to treat the patient, because you can, there's no rejection if I take from you and generate anti-ES cell and use this to generate functional cell for the treatment, right? So also, actually, many people know this first time cloning of a primate, okay, cloning of monkey, and the trick they use is to inject the demethylate to remove the gene barrier. Okay. So then, given this, we found a new imprinting and that involving X inactivation barrier. So we thought maybe we can overcome both by combining the increase the efficiency. One is the response of pre-implantation, one is the response for post-implantation. We did that by using this knockout as a donor and inject kinin demethyl to remove the barrier. Now we can achieve the highest cloning rate from 1% to about 24% in mouse. However, it still have a big placenta. Okay, and the reason is because the other imprinting I mentioned and 27 methylation imprinting. So basically, these genes involved in placenta development, they have double dosage. Okay, in fertilized egg, they have a single dosage. So that's why, well, and that's the hypothesis. We actually proved that's the case in this experiment. So basically, this particular gene encoded responsible for transport amino acid for nutrition of the placenta. So in the SNT, you have a double dosage because the loss of imprinting, loss of the silencing of maternal allele, you have two dosage. Therefore, you have big placenta. We can overcome this by knock out the female allele. Therefore, only have the male one expressed. So therefore, you have normal dosage. So basically, this demonstrates this new imprinting 27 methylation is a major barrier to prevent post-implantation development of a cloning animal. So in the next couple of slides, I will show you our effort to translate our work. So I mentioned early on, EZH2 is an enzyme, methylated H3 less than 27. So it's important to control imprinting, important to control polycount. So there's many studies, many years ago, report this gene is overexpressed in cancer, in almost every type of cancer. So it's an interesting target. And other study, we also identify another enzyme, but one that methylated 79, we show that it's involved different leukemia. Okay. So use these two different histone methyl transfers, we basically want to know whether this new family of enzymes are subject to chemical inhibition with small molecules. So we perform a no input throughput screen, use a gel-based assay. As you can see, this is the EZH2 enzyme, and these different chemicals inhibitors added to this. As you can see, for the different enzymes, EZH2, that's polycom, this .1 sap 7PRMT1. So this screen, this is secondary screen, we found something general. This chemical can inhibit every enzyme, every muscle transfer. But on the other hand, if when this two compounds only inhibit the EZH2, okay, but not the other. So basically, this leading us to ask whether we can take this further to develop drugs. So in 2007, we founded a company called Epidem together with Bob Horwitz, who is a professor of MIT. He's also a Nobel laureate. So this funding in 2013, this company IPO, and 2020, we have FDA approved the drug that treat for the astrocytoma and follicular lymphoma treatment. So to summarize, basically during the last almost 25 years, we basically identified a long of class of different epigenetic enzymes. We contributed the mechanistic understanding of three classic epigenetic phenomena: polycomb silencing, genomic imprinting, X activation, and identify.
Recording stopped.
Yeah, very okay. Two major barriers, cloning, and we translated the inhibitor of EZH2 for cancer treatment. Thank you. So basically, common element yeah. All right. Thank you.
Thank you, Dr. John. Yeah, thank you. The very interesting research. So
做的更精确，更那个 specificity 和那个 sensitivity 可以更高一些。所以呢，我们就取了这么一个名字。但是后来呢，就是不光是做产品开发，还有 manufacture， 然后我们自己也做一些销售。我们公司呢，基本上是那个1996年成立的，然后我们已经有26年了。有时候想想，我要26岁多好啊！然后呢，我们现在有大概100个那个employees， 然后我们重点呢还是在产品开发和技术的创新，所以我们现在有27个那个专利，然后我们公司是注册是 minority 少数民族 woman owned business。我怎么气不动呢？这是我们公司的 building， 我们公司现在有4万个 square feet， 现在呢我们在扩建，马上呢就去，现在这段时间就是在做就去安排，大概准备我们能够扩建到6万个 square feet， 所以只能做这个事情。这是我们后面的 view， 这是我们的 warehouse。warehouse 你可以看到我们有很多的生产，包括塑料啊这一类的东西，包括我们的抗体、抗原都从国内来的。我们的产品呢，就是我们的卖点吧，就是那个 Made in the USA 然后我们现在有50多个那个产品，而且绝大多数都是那个美国的 FDA 510K clear， 就还有那个 CE market。我们的重点呢还是在做 POC point of care 和那个 home use。这是我们代表的一些产品，这个呢也是我们的专利产品。我们的那个 cassette 呢是我们取了一个名字叫 driver flow， 主要是在 lateral flow 的基础上呢，我们加了一点，就是有一点压力，可以帮助它就是向下、横向和那个向下的一些那个 pressure， 就让它混合的更加均匀，走得更快。尤其是在有些sample比较粘稠的，像 saliva 这类的，就是唾液，它可以就是让它就反应的更完整，然后时间更短。这是 driver views， 我们呢在这个里边呢用了我们的那个 driver flow 的 technology， 里面有些结构吧，就是跟普通的那种那个 driver views 的一些那个它有一些不一样。是这现在呢也是一个方向，就是那个用 reader 就是 electronics， 就是这个叫。我们现在也做了一些产品，比如说像流感，像 COVID-19， 还有那个 SHRP-A， 包括一些 smart reader 呢，我们现在这是我们的一些 marketing 的 flyer， 就是这是我们专做的 cassette， 然后有那个就是 smartphone connect 跟那个 device 去连接在一起。这个呢就是 QAD， 就是流感的那个东西。然后一个公司呢，就是如果没有那个质量的话，那个公司根本就不应该存在，因为太人了。还有呢，但是那个公司呢，如果没有产量呢，这个公司呢就长不大，甚至于就活不下来。那这个呢，能够做到这2点呢，要全靠我们的团队。这是我们的 marketing sales 团队，就产品做出来了以后，你要卖出去，对不对？那这个我们的团队呢 ，sales marketing 团队起了很大作用，看他们也挺开心的。这边也是我们前面的某意思 ，marketing sales 呢，还有一个好处呢，他们是去参加那个trade show 的时候有一些放，这是他们参加的一个那个化妆晚会，就是那个我们看了半天都认不出来了。那么在团队里边呢， 家庭的成员，包括先生或者是小孩儿子、女儿，这些都是一个很重要的因素。有了他们的支持的话，也就实际上也是公司的很重要的一个稳定的因素。那么我先生呢也是做这一行的，而且他也是在美国拿了 PhD 博士后，所以我们的专利有好多是由我先生参与的。就两个人有人讨论的话，有些东西 idea 就会1+1不等于2，所以就是会有些新的火花出来。那么下面是我的2个女儿，双胞胎，他们现在已经长大了，这是他们小时候。那么小的时候呢，嫌他们麻烦，也要2个双胞胎干起来很累。但是现在呢，他们俩是我们公司的顶梁柱。一个呢管销售，一个呢是做财会。他们呢是我们公司的很重要的一个稳定因素，因为他们跟着公司一起长大，他们了解公司各方面的情况。除了产品开发quality assurance 他们不能做以外，其他的各个部门如果是有变动的话，他们马上就有顶上去，说不定还会做得更好，因为他们了解的东西更多。然后要出产品呢，需要 equipment。我们的 equipment 呢，从老的、旧的到新的，到那个自动化的，还是有一些。所以，因为产品的质量呢，实际上自动化的那个机械的话，对产品的质量也是一个保证，因为它不受人的那个 human error 的影响。这是一个全自动的那个 memory 的 folding 机器，这是一个全自动的那个包装机。像这个机器我们用这个是全自动的组装机，这个呢是我们的一个抽干机，是一个就是简单的 lyophilizer。现在呢，我们这个 field 最初期的时候，大家有些方法也挺土的，就是用吹风吹，就是一大块湿的东西用吹风吹，这样会有一些避免效应。所以就不能保证用那个真空抽干冰冻的，那么可以在短时间内抽干，而且呢可以避免那个边缘效应，这样呢就是产品的个体之间 lot to lot 之间的 variation 就会非常小。这是一个，我们公司呢有27个那个 patent， 所以呢就是还是下了一些时间，下了一些功夫。美国的那个专利局曾经拜访过我们公司，他们在那个组织了一个12个人的一个团体，就是专门去拜访了一些公司，去看他们专利的执行的情况。那么我们算是其中之一，他们头上戴的帽子是我们的专利的一个礼品，那边专门的一个 logo 在。他们实际上他们非常认真。实际上，产品呢，专利是我们的产品，但是批的专利是他们的产品，所以他们来了以后，你看每一个他们自己批的专利，这都是他们批的。他看着这个产品特别开心，看怎么样走，怎么样动，就是这个产品怎么 work， 就是这个他们就是花了很多的功夫去那个研究我们这个专利，根据我们的专利做出来的产品，他们也挺高兴，这是他们的成就。这也是这个那个女士，她也是就是听着看我们都是觉得非常有意思，她也挺骄傲的。我们的 customer， 我们 customer 呢不能说太多，因为这个涉及到那个 trade。那我们的那个 customer 有几个都是全世界前10名的大的那个 diagnostic。其中有一个，就这个公司呢，他们不在乎我们提他们的名字。这是 Siemens， 就是西门子。西门子呢，我们跟他们做了10多年了，而且我们有2次拿到他们的奖状。一个呢是那个，一会儿再说了。我们其他的有些公司呢，都也合作的挺好的，主要我想并不是因为我们的价格特别低，而是我们的质量符合他们的要求。 奖状呢，我大概拿了一些，其中有一个我想提的呢，就是美国的 Small Business Administration。在我们公司，这个呢，我为什么要提呢？就是说，我们想创业，就是有计划要创业的朋友，就是可以先跟那个美国的那个 Small Business Administration 跟他们联系，因为他们有全套的可以那个就是 consulting 的那个一些service， 他们有从你公司的注册到你的财会，到你的那个一直到你的所有的有些很重要的 human resources 这一类的东西，它都可以给你提供帮助。最主要的呢，你3年以后，3年之内他不管你，3年以后他给你提供你的那个，反正就是贷款的那个，这哈，就是有他们做担保的话，那么银行会比较容易给你贷款。所以我们公司呢，实际上在3年以后也确实得到了他们的帮助，像 Bank of America 还有其他有些银行都给了我们上百万的一些贷款，这个要靠我们自己拿不到的。有那个 Small Business Administration 做那个担保的话，他们也就放放心心的就把这个钱给我们了。用了这笔钱呢，我们买了我们的第一个那个 building， 然后我们第二个 building 呢也是那个银行通过 Small Business Administration 给我们买到，所以这一点呢，我就是给大家提一下，也许可以有一些帮助。那么在2002年呢，我拿到一个就是 Minority of the Small Business， 在那个圣地亚哥的 Small Business Administration， 这是他们的。这就是那个西门子的那个给我们的，我们拿到2个西门子的奖状，一个呢是那个 Outstanding Supplier， 这个 Outstanding Supplier 呢是有一点故事，但是我想我们今天时间不够，我就不讲太多了。其中呢，主要是因为中间那个产品曾经出过一些问题，我们跟他们一起，他们呢就是最开始的当然就是你 manufacturing 是你的产品的质量的问题。后来我们跟他们一起就做了很细致的那个study 那种调查工作，最后证明是他们的那个control 他们的那个 standard 的问题，把那个问题解决了以后，那么10多年就是那么多年以来，我们的那个 consumer complaints 由于我们产品造成的几乎是零，所以呢，他们给了我们这么一个奖状，这也是来自鼓励的。最近呢，去年前年我们又拿到一个奖状，这就是 Woman of Business Supplier， 所以呢，我们曾经在那个西门子拿到2个。还有一件事我想提一下呢，就是我这里没有放，是有一个奖状呢，是那个American Citizen Against the Lawsuit Abuse， 这是我拿到一个奖。这是为什么呢？他们这个奖很少有人能够拿到，那是因为我们呢，我的原则呢就是我不去惹那个事儿，但是呢，如果有人来惹我的话，要打我就打到底了，花多少钱也没关系。这是因为一个 HR 的一个 employee 是一个是一个伊朗的一个 scientist， 主要是他没有提 manager， 另外一个女的提了，所以他就说我们 discrimination。结果呢，他就要去告了一阵，就是说如果你们不给我提 manager， 或者是你要给我补偿，关键他是要补偿，如果没有拿到补偿的话，他就告。那么我觉得他这完全是无理要求的，you have no case， 如果你愿意告的话，你告出来。结果呢，他就去告了，告了以后呢，然后我们发现，我们就做了一些调查，发现他是一个惯告，他告了6个公司，他走到哪里告的。但是呢，那个公司呢是没有，那些公司呢都选择跟他 settle， 就是赔他的钱，从几千块钱到几万块钱，他拿了钱就高高兴兴走了，要到下一个公司继续告。 所以呢，我就想，就是大概是到了未命除害的时候，我不能让这种继续这样下去。你想，他这样下去，这种东西不能鼓励，到了我这里也就应该 stop 了。因为一旦他告上法庭，一旦有了记录，他也不能再做了。最后我们赢了，判了他6000块钱，所以他赔了我们。这个事情呢，我就是讲一讲，给大家做一个借鉴。那我今天就先讲到这里。下午呢，我们的梅会长呢还有一个 section， 如果大家有别的问题呢，我想我们留着下午再讨论，就不耽误大家时间了。谢谢大家。
Thank you very much, Dr. Wang. So this marks the end of the morning sessions. Thank you very much, everyone. Hope you enjoyed the exciting lectures. And we have lunch box for everyone. Please grab some over there, but please stay in this area having lunch, and because other areas are office areas for other companies. So please get the lunch box and come back. And in the afternoon, we'll get into 4 special sessions. So please refer to the agenda on your flyer and join the one that you are interested in. Thank you.
就是筛一下吧，把它那个就是哦，这种。哎，是宋老师你好，你好，你好，我们是领导的，你可以用我的电脑来，我看了你信息，可以用我电脑把东西放在，是吧？对，对，我现在是等到第2个，现在就是第一要他们现在还在上。你到那个你要地方你也以为我们待会儿就可以加2号，还都在。好。
咱们吃了。